All right, one popsicle later, and I'm ready to move on. You guys, I have eaten an ungodly number of popsicles this week. So, we want to look for if there is a relationship in this triangle between the side lengths of these two, AB and, AB and AC. But there's also a relationship between AB and BC. So when we think of this 45, I guess we don't know 45, 45, 90 yet. We know this has an angle of 45 degrees and an angle of 90 degrees. But we can pretty quickly realize that that means this one is 45 degrees as well by subtraction. And we know that if the angles of the two corners here are congruent, then that's going to mean that the sides opposite them are congruent. And that makes this a isosceles triangle. All right, that's one of the reasons we're going to learn about it, because 45, 45, 90 triangles are isosceles, and we see them fairly often for that reason. Because of that, we don't want to have to do the Pythagorean theorem every single time to find the side lengths. Instead, we can find a shortcut way where if we know one side of a 45, 45, 90 triangle, we can use it to find the other two sides with a relationship that we already know. And here's how that is going to work. If I know that this side and this side are the same, I can call them both x. And I can use those two side lengths and this hypotenuse with the Pythagorean theorem to help me find an expression that represents the hypotenuse. So if I say x squared plus x squared, a plus b, equals my hypotenuse squared, I can combine my like terms, make this 2x squared equals c squared, but I don't want c squared, I want c. So I'm going to take the square root of both sides. It gives me c equals the square root of x squared is x, but the square root of 2 is not a whole number, and in order to keep it simplified, I'm going to call this x square roots of 2. And I'm going to call side AB x square roots of 2. And what that means for me then is I am able to say that there's a pattern I notice. There's an x in each side. This hypotenuse just has that value multiplied by the square root of 2. What that means for me is I can use one side of a 45, 45, 90 triangle to find the rest of them, right? If I know one leg is 7, and I know the other leg is 7, I know that because it's going to be an isosceles triangle, then whatever number I use here, the hypotenuse is going to be that number, or x, multiplied by the square root of 2. So all I need to do for yz is say that that is 7 square roots of 2. And that is all three sides of my isosceles 45, 45, 90 triangle. Right? If I look at JKL and I have 12 root 2 as the hypotenuse, then I know that the side lengths can be x and x, that number in front of the square root of 2, which is 12 and 12. And I can do this, like I said, for any 45, 45, 90 right triangle. I also have a rule for 30, 60, 90, another very common type of right triangle. This one is really common because if we start with a 60, 60, 60, an equilateral triangle, and we draw a line down the middle, all of a sudden we have a 90-degree angle. We have that 60-degree angle that was originally there, and then we have this 60-degree angle at the top is going to cut in half to become a 30-degree angle. So this is another common type of right triangle because it is an equilateral triangle cut in half. And we want to be able to make a relationship between these side lengths so that we don't always have to use the Pythagorean theorem to find out the lengths of the side lengths. So let's think about this. We have this triangle, and I want to find a relationship between the sides. I'm going to start with the smallest side, and I'm going to call it x, because I don't want to have to use fractions of x, so I need that smallest side to just be x. But if I think about this, this started as an equilateral triangle. Then I cut that base, in half. So if this piece is x, well, that means that this piece is also x. And that means we can make an assumption about every side of this right triangle. Every side of this right triangle is going to be 2x units long. So we're going to write that the hypotenuse is 2x. We've got the short side is x units. The hypotenuse is 2x. We just need to find out the length of the third side of our 30, 60, 90 triangle. We can do that using the Pythagorean theorem. So we will take our short side, x squared, plus we don't know b, so b squared equals 2x squared. And we'll solve that. So x squared plus b squared equals 2x squared is equivalent to 4x squared. Then combine your like terms, solve, right? We've got minus x squared, b squared equals 4x squared minus 1x squared is 3x squared. And then we'll take the square root of both sides. And just like last time, the square root of x squared is x, but the square root of 3 is something we can't simplify. So we're going to leave it as x root 3. And that will be how we represent the length of the third side, in this case, the medium length side of a 30, 60, 90 triangle. And this will be true then for every 30, 60, 90 triangle. We can use it to find out different lengths of the triangles. So if I have a 30, 60, 90 triangle right here, and the shortest side, we can tell it's the shortest because it's opposite the 30-degree angle. If the shortest side is 6, the hypotenuse will be twice as long. That'll be 12. And then the middle length side will be the x root 3 side, this side right here. And if 6 is x, then we can call this middle side 6 root 3, just like that. For this next triangle, we have triangle TUV, and we know that the medium side is 9 root 3. That means that our short side is just the number in front of the square root of 3, that's 9. And our hypotenuse is our short side multiplied by 2, that's 18. So again, we only need to know one side of our right triangle in order to find the length of the other two sides. All right, we will do the rest of the examples here in the next video.